Hey everyone, welcome to Calculus. Today we are going to go back to the graphs of f and f prime, and we're also going to add the graph of f prime. We'll look at characteristics of f, f prime, and f double prime, and we'll be analyzing some more graphs, except we're going to add one new characteristic that we haven't talked about so far. So far we've talked about if I have the graph of f, and f is increasing like it is right here, f would be increasing, then the graph of f prime should be positive for that same x interval. And then we also looked for how to identify relative maximums by looking for wherever f prime would change from positive to negative. We had a chart where we put all this information. Well, now we're going to add a new characteristic of a graph. So erase everything here. Our new characteristic is going to be concavity. So we'll use the reference in your notebook, page 112, 113, if you want to look and read. Those are some, it's got good summaries if you want to read it later and take notes later, but page 112, 113 is what we're referring to today. Then we'll pull some examples from Delta Math, because that's what your assignment's like. So on page 12, you'll see a description of something that's concave up versus concave down. Concave up meaning that it can hold water. So this picture, concave up. Then concave down kind of looks like a frown or spills water. So concave up holds water, concave down looks like a frown. So, and you'll see me abbreviate concave up like C up, which actually looks like cup, and a cup holds water. Concave down, you'll see me abbreviate C down. And when you first started studying curves, we saw quadratics, which would just have either one curve that was only concave up or only concave down. But then later on, we saw some curves that had multiple things going on, where we had a part that was concave up, and then concave down, and then concave up again. And so it'll be our job to identify the x point where that concavity changes. And so that x point where concavity changes, see where the graph is going from concave up to concave down, that's referred to as an inflection point. Inflection point is where a graph changes concavity. Now, it can be tricky sometimes to find that by inspection. Now, this graph's already labeled, so it might be easier. But let's say I were to draw a graph like this. Might be hard to figure out, okay, well, is the inflection point right here? Or is it right here? Or is it right here? Like, where exactly does the graph go from being concave up to concave down? Is it right here? So since it can be tricky to find that stuff with the naked eye, we can use function analysis. That's where calculus comes in handy. So we can use our knowledge of derivatives and the characteristics that those derivatives have. So this is page 113 in your notes packet. And an important part that we want to look at, get my little yellow out here, is that f prime is increasing on the interval and concave down. F is concave up on an interval if f prime is increasing. And then if f prime is decreasing on the interval, then f would be concave down. You'll see that summarized here as well with the second derivative. If f prime is positive for all x in an interval, the graph of f of x is concave up on that interval. If f double prime is negative, the graph will be concave down. And then if the graph of the second derivative is equal to 0, then the graph will have no concavity. So we'll look for inflection points, and these directions down here are how you find them algebraically. So we're not going to look at that quite so much today, but I took this information and summarized it on a chart. So you will want to write this down, add this to your chart. So here is the chart that you're pretty familiar with at this point. So far we've been looking at the first two rows, and looking at how to tell if f is increasing, you look at where the derivative is positive. If f is decreasing, you look at where the derivative is negative. So these first cells you're already familiar with. And notice like nothing is happening with the second derivative on those first cells. But if the original function is concave up, the derivative is increasing, and f double prime, that's supposed to be that is a positive. It just might be hard to see. So f double prime would be positive. If f is concave down, the derivative is decreasing, and the second derivative is negative. And if f has an inflection point, that's again where we would change from concave up to concave down, so like an inflection point right there, you would see a critical value in f prime, in other words, a change from increasing to decreasing, or vice versa, So f prime could change increasing to decreasing or decreasing to increasing. And then f double prime, you would see a change in sign. So you would notice, like on the graph of f double prime, the graph would be going from being positive to negative or negative to positive. All right. And so with this information, you're going to have questions that ask you about f or about f prime or about f double prime and concavity. And you'll be asked this in a bunch of different ways. So we are going to actually work through some of the similar questions that you're going to see in Delta Math, and just make sure there's nothing else I need to tell you before we move on. Nope, Delta Math example. All right. So in Delta Math, you'll be asked questions 1, 2, 3, 4, 5 different ways. So if you look in the first section, you have to find you have to label the graph of the function, the derivative, and the second derivative. So I've got 3 different graphs here. I have to figure out which one's a function, which one's a derivative, and which one is the second derivative. Now you can use whatever strategy you want, but I like to start with the thing that I'm most familiar with, which is identifying increasing and decreasing intervals. So first of all, I'm going to try to figure out if something is a function and if it's a derivative. So I know that if like the original function is increasing, then the derivative would need to be positive. Likewise, if the function is decreasing, the derivative will be negative. So the first strategy I'm going to use is I'm going to try to find a function and a derivative of that function. So I look at this first one and I notice that this is increasing until about 1. So if this were to be the function, if this were the original function, then I would need, if something were a derivative of this function, then it would need to be positive above the x-axis until about x equals 1. Well, this graph is positive, but then it becomes negative way before x equals 1. So this would not be the derivative of that if this is the original function. And then this function is positive, but only until -2, and I need the derivative to be positive until 1. So this would not be the derivative of this function. So that means maybe this isn't the original, maybe the first graph isn't the original function. Okay. So let me try this one. Let's try making this one, second one, the original function. Now, if this graph is the function, I notice that it is decreasing until about x equals, right before x equals -2. So then I'm going to look on the derivative. If the function is decreasing, then I need to look for where the derivative would be negative for that same interval of x. So from -9 until about -2.5. Oh, look, this graph is negative until about -2.5. And then it's positive after that. And then this graph would be increasing, the function would be increasing, and then the derivative would be positive. So I'm thinking that's the function, this could be its derivative. Okay, so that could work. So then we have to check, okay, well, is this one a second derivative? Well, here's what I know about my second derivative. If my first function is concave up, then the derivative will be increasing, and the second derivative would be positive. So so far we've labeled function and increasing. So let's double check what we have. Let me get a different color here. Looks like my original function might be concave up for about like maybe right here. Like I said, it's hard to spot the inflection points by eye, but I'm gonna say like concave up right here. Like concave up here. So then I need this, if concave up, then my derivative should be increasing for a while, increasing until I get to 1. So increasing. So does this look like it's concave up until about 1? Yeah, I could say there would be a change to concave down next part. Okay. So I could say it would be that, concave up until about 1. Okay. And then I would need to see on that same area, is f double prime positive for that? So I'm looking for f double prime to be positive until about x equals 1. Positive until about x equals 1. Not happening here. Okay, well, since that's not happening, let's see what my other option is. We have established that the graph on the left is a derivative of the graph on the right, but maybe the graph on the right itself is the first derivative, and a derivative of the first derivative could be the second derivative. So it could be that this is the first derivative, and then the graph on the left would be the second derivative. So if that were true, then let's check the concavity on what is potentially my original function. Well, the original function looks to be concave down, maybe until about, I don't know, 3. So concave down from -9 to -3. So if this is the original function, then the derivative, let's see, concave down, the derivative would be, first derivative would be decreasing, and then the second derivative would be negative. So then that would mean f prime should be concave, no, should be decreasing from -9 until -3. Hey, look, it's decreasing -9 until -3. And then the original function is concave up afterwards. So concave up, my first derivative should be increasing. It's increasing. So it was concave down, then it was concave up from -3 to 9. And then this one is also increasing. The first derivative increasing from -3 to 9. And then the second derivative, let's see if this was, the original was concave down from -9 to -3. Then the second derivative should be negative from -9 to -3. And oh my goodness, look, from -9 to -3, negative. So it looks like we have found the original function to be the bottom one. That's the first derivative, and that's the second derivative. I'm going to submit my answer. Yay! Now, those take a little bit of time, so you will have to think your way through them. But you only have to do 2 of them. Now, the second section I really like, so let's look at it. All right, so we have the second section, and we're given a graph of f, and we're going to be asked to determine all values of x where f has an inflection point. So we're looking for change in concavity on the open interval from -9 to 9. Now then, it's like if you drag the yellow point, you'll see the graph of f prime plotted in real time. So what I like to do is I like to just hold this down, and the orange graph is f prime that's being plotted. So this is going to allow me to look at the original function, trying to get the whole thing plotted, and the derivative at the same time. And that's going to help me to really, really, really be sure about where my inflection points are. so I don't have to guess by looking at the graph. Okay, so we're looking for inflection points on this one, so let's pull up our chart. Inflection points happen on the original function where it changes concavity. On the derivative, we need to see a change increasing to decreasing or vice versa. So let's write that down. So for F, inflection points happen at a change in concavity. For F prime, inflection points for F, if F is changing concavity or if F has an inflection point, then F prime would have a change of increasing to decreasing or vice versa. That's a spot where that's going to happen. Okay, so change in concavity. So if I just look at the graph of F, I see that it starts off being concave up, and then at some point, it starts to be concave down. So if I'm just looking at the graph of F, I'm guessing like between here and maybe this is where it changes, start being concave down. Maybe it starts at this X value. Maybe it starts at this X value. It's kind of hard to tell using the naked eye exactly where my graph changes from being concave up to all of a sudden being concave down. So I'm going to use my graph of F prime to help me. So then I look at the graph of F prime, and I see that the graph of F prime increases, 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 and then all of a sudden starts decreasing. So right here is where it changes from increasing to decreasing, which is an X value of -1. So right there, that is an inflection point. So far I know that there's an inflection point at X equals -1, but there could be more. So if I hit a comma, then another box will open. So let's look. F prime changes decreasing, 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 and then it changes to increasing one more time. Right, decreasing changes to increasing right at X equals 3. So right there, there's another inflection point because there's a change decreasing to increasing on F prime. And then increasing, F prime is increasing, F prime changes to decreasing right at 5. That means the graph has another inflection point at X equals 5. And then if you look back at the graph, you can see, oh yeah, that's concave up, concave down. So I got to list these: -1, 3, and 5. And I'm giving X values again. Isn't that my answer? Awesome. In the third section, we are looking at concavity visually. So this time, if I'm tracing, now I have the tangent lines that are being sketched for F prime instead of the actual graph of F prime. So what am I doing now? Given the graph of F below, determine all the intervals where F is concave down. So when F is concave down, then the derivative will be decreasing. So I'm just going with this pink line because that's what information I have. I don't have any information about F double prime. I only have information about F prime. So let's write that down because it does help to look at what I'm looking for. So when F is concave down, F prime is going to be decreasing. Now, since I have the graph of F, I can kind of have a good idea of where it's concave down. Like it looks like concave down, and then some point starts to change to be concave up. But I'm going to guess, like right here, concave up, and then maybe this is concave down for a while, and then changes concave up. But I need to find those exact values, and I can do that by looking at where the derivative is decreasing. So I'm going to pull my derivative here. All right, so I'm going to be watching these values of the derivative. So these values right here, right where it says undefined, I'm going to watch how those change as this moves. So concave down, I have a value of 3.03. Those values are getting smaller, smaller. They're 0, and now they're negative, more negative. Negative 1.5, negative 1.6, negative 1.8. They keep getting smaller. Negative 1.9, negative 1.94, smaller. Negative 2, even smaller. Negative 2.02, negative 2.09. These are smaller numbers. Negative 3, negative 4, negative 4.3, negative 5, negative 6. Oh, you see how it was negative 5 and then went to negative 6? Right there. And then it started getting less, like started getting bigger again. So right there where it changes, where it hits at negative 6. Negative 3. So it looks like f prime is concave down all the way until negative 3. So I'm going to say negative 9 to negative 3. And then later, now you can use u or you can use the word or. Delta Math will accept either. I do have this other area I want to check out. So I'm going to trace. Okay, I'm looking for, see these values. Now the slope values up here, those are getting larger. I need to start observing where they're getting, when they start getting smaller, that's where my next interval is going to start, negative 3, negative 2. Oh wait, did they start getting smaller? Yeah, they're decreasing right now. Oh no, those are getting larger. Sorry, negative numbers. Those numbers, larger, 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 larger. Okay, now they're getting smaller again. So where did that change happen? 0, smaller, smaller. Getting smaller again. Okay. So let's see, they're getting smaller, 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 smaller. Sorry, they're getting larger. Hold on, go back. They're getting closer to 0. So they're getting larger, 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 larger until we get to 0. Right there, 0. Now those slope values are getting smaller. So I'm going to say right at 1. So from x equals 1 until now I have to figure out where those slopes, stop getting smaller. Negative 1.8, negative 2, negative 2. Negative 3.5, 3.7, 3.9, negative 4. Oh, went down to negative 4 and then went back to negative 3.9. So right there at 5, that's where it stops being concave down. Right there. 2, 5. Okay, so I'm going to enter this in, and I'll show you the other way that Delta Math will accept this. Negative 9 to negative 3. And then if I use the union, 1 to 5, I'll submit. That's right. But you could also use the word or. You can use either one. That's fine. All right, going into the next section. Determining signs of f, f prime, and f double prime. So here I have value, let's see, this is a graph of f. I have to figure out whether f prime of 0, and f double prime of 0 are positive, negative, or equal to 0. So remember, I've got the graph of f. So the first thing I need to do, oh, the other thing that they've done, they've pointed out where all the inflection points are, which is really nice. All right, so f of 0, I can figure out by just finding f of 0, and it looks like, there's actually a point, f of 0 right there. F of 0 equals negative 2. All right, And then what is f doing? Well, f is, let's see, so f of 0 would be negative, because negative 2 is negative. Now, what is f prime doing? Well, let's think about what I know about my function. Right here, it looks like this is on an interval where f would be increasing, 0 is. So if f is increasing, then f prime is going to be positive. So I'm going to say f prime is positive. F prime is positive. And then let's see, what's happening with f double prime? Well, there's an inflection point right here. So let's see what happens with an inflection point. At the inflection point, for the second derivative, there's a change in sign. So there's a change from positive to negative or negative to positive. So whenever you see a change in sign, positive to negative or negative to positive, then you would also see the second derivative to be 0. So, whoa, don't X out of it. We're going to say the second derivative is going to be 0. Yay! And then back on to the last section, analyzing the derivative graph level 2. All right, so here I have the graph of f prime. Ooh, this time I have f prime. Determine the values of x, if any, where the function has an inflection point. Okay, so inflection points. I have the graph of f prime. So I want to know where f has an inflection point. Then I need to look for where f prime has a critical value, which is a change from increasing to decreasing. So I'm pretty much looking for relative max or min on f prime to identify inflection points on f. So anytime there's a relative max or min, I'll have my answer. I can click back in there. Also, it looks like there's one right here at -5. Looks like there's another relative max at 6. No, not 6. I need that x value. 0. At decreasing again, no change, still decreasing. And then right here, decreasing to increasing at 6. So -5, 0, and 6. Let's see if this works. There we go. All right, so good luck with this assignment. If you need anything, let me know. Have a great day, and I'll see you.